Hello, my name is Benjamin Braun, and this is Joe Rogers. Today we're going to be talking about a language we developed for expressing primitive recursive arithmetic. So primitive recursive arithmetic language, we call it PRALine. So why would one want to write programs in primitive recursive arithmetic? Well, primitive recursive arithmetic is known to be consistent, which means that we can talk about with a very well-founded basis whether a program in primitive recursive arithmetic is correct. We can prove things about primitive recursive arithmetic relatively easily. And furthermore, primitive recursive arithmetic is actually relatively expressive. All these functions here can be expressed in primitive recursive arithmetic, of course, basic arithmetic, but also minimum and maximum, so order comparisons can be expressed. And also we can do things like divisibility and is prime. So our objective is to take primitive recursive arithmetic and develop a language that expresses it. And we want to develop tools which allow us to take primitive recursive arithmetic code and perform queries on it, so to prove things about primitive recursive arithmetic in an automated sense. So here is some example PRALine code. It defines the addition function. The way we define functions in PRALine is using something called relational notation. So we define the relation add to contain tuples x0x, which basically means x plus any x plus 0 gives you x, and also to contain tuples where x plus y plus 1, so where the tick means successor, x plus y plus 1 is the same as x plus y plus 1. Right, so the tick just means add 1. And so then we'd like to evaluate what is 2 plus 3. And so if we were using a proof system, we would expect that the output would be something like this. First it would prove that 2 plus 0 is 2. Then it would use that to show that 2 plus 1 is 3, using the second case. Then that 2 plus 2 is 4. And then finally that 2 plus 3 is 5. And this would be a proof. These 4 lines would be a proof that 2 plus 3 is 5. So we can parse this example PRALine code as follows. A program which has a function and a query. The function is the add function. The add function defines 2 cases. The order matters. The first case defines the case where the first argument is general, but the second argument is 0. And in that case, it should return x. So this case handles cases where the second argument is 0. Whereas the other case, which is only used if the first case is not applicable, which means the second argument is non-zero, takes x and then y prime and returns xy add prime. We evaluate a query, which basically just says add 2 plus 3 and give me the result of that. In general, a program written in PRALine has this abstract syntax tree. A program has one or more functions. Each function has one or more cases. The order matters. Each case has a list of arguments, which can be identifiers or literals, and an expression, which is what to return in the case that this case is matched by the inputs to the function. Queries can be either function calls, which I've shown before, or they can also be inclusion tests. So we can check whether a certain tuple, say 2, 3, 5, is in a certain relation. So how do we implement a tool chain that allows us to go from PRALine code to the proofs I showed a second ago? Well, first, we take PRALine code and we use a scanner to chop it into tokens. Those tokens can then be grouped into non-terminals using a parser. That creates an abstract syntax tree, which is visited by our Java emitter. That Java emitter outputs Java code, which implements the primitive recursive functions defined in the PRALine code. We then run Java on that output Java code, run Java on the output class files, and now the runtime of Java will output our proofs. So now we're going to show our system in action. Here is a piece of PRALine code that implements addition and multiplication. We already showed the code for addition, and then we're going to just evaluate what is 2 plus 3. We can also define multiplication function, so x times 0 for any x is 0, and x times y prime can be defined as x times y plus x. That's what this line says. And then we're going to check, is the tuple 2, 3, 6 in the multi relationship? Or in other words, is 2 times 3, 6? So we can run our tool chain by first making the tool chain's parts, and then we can run that test file. And indeed, the output at the top is what we expected for a proof of 2 plus 3 is 5. So it uses 4 steps. First it shows that 2 plus 0 is 2, then 2 plus 1 is 3, then 2 plus 2 is 4, and then finally that 2 plus 3 is 5. Multiplication is more interesting. We sequentially prove a number of statements about multiplication and the addition function, which together lead to a proof that 2 times 3 is 6. So the tuple 2, 3, 6 is contained in the mult relationship. To show an example of another function, we can look at the less than function. So we define the less than function so that over natural numbers, any natural number x cannot be less than 0. So that means x0 should return 0 on the less than function. However, if that case is not met, so in other words we fall back to the second case, then the second argument cannot be 0, which means that 0 is less than any non-zero natural number. So 0x1 is the second case. And in general, to determine whether one number is less than another, we can subtract 1 from both arguments and then run the less than function on those new arguments. So we test 5 values. Let's run it. So first, we just show that 1 is indeed not less than 0, thankfully. That 0 is less than 1. So both of those two are just by axioms. No proof is needed. But now, we show that 3 is less than 4 in 4 steps. First, we use an axiom above. Then we show that 1 is less than 2, and then 2 is less than 3, and then 3 is less than 4. So that's a proof that 3 is less than 4. Also, we show that 3 is not less than 3, also in 4 steps. Scrolling down a little more. We show that 4 is not less than 3. So this at least shows that our system can be used to perform certain simple primitive recursive arithmetic proofs, and more complicated examples can certainly be done. However, our language actually allows you to express functions that are a little bit outside the range of primitive recursive functions. Relational notation can describe functions such as the Ackermann function, which is known not to be primitive recursive. So, in a sense, we might actually be able to offer proofs for programs which are broader than primitive recursive arithmetic. So this is interesting, but primitive recursive arithmetic is definitely within the grasp of this language, PRALine. So in conclusion, the PRALine language can be used to describe primitive recursive functions, and it can be used to prove things about those primitive recursive functions. Our code is extensible, which means that future work can be done to improve the functionality of the PRALine language and to offer other proof-type features.